Limit is y goes to 0 of 12 sine squared of 2y divided by tangent of 3y. The first thing we're going to do is try plugging a 0 in for each of the y's. That will give us 12 times the sine of 2 times 0, quantity squared. Remember to do the square after evaluating the sine for sine squared. And then divided by the tangent of 3 times 0. So in the numerator we have 12 times the sine of 2 times 0, which is 0, quantity squared, divided by the tangent of 3 times 0, which is a 0. The sine of 0 is 0, so 12 times 0 squared divided by the tangent of 0 is the sine of 0, 0, divided by the cosine of 0, 1, 0 over 1 is 0. 0 squared is 0. 12 times 0 is 0, and we end up with a 0 over 0 indeterminate form. Since we have trig functions of different phases, we will want to make use of the identity that limit as theta goes to 0 of the sine of theta divided by theta, which equals limit as theta goes to 0 of theta over sine theta. It could be either version, and it's equal to 1. To make use of this identity, we have to take any non-sine cosine functions and turn them into sines and cosines. In the numerator, everything will be left as is, but in the denominator we have a tangent of 3y, which will be the sine of 3y divided by the cosine of 3y. Since we have a fraction in the denominator, our next step will be to reciprocate that fraction and multiply it, so we'll have 12 sine squared of 2y times the reciprocal, which will be cosine of 3y divided by the sine of 3y, and we multiply by that reciprocal. Let's put the original expression over a 1 so it also looks like a fraction, and we have the limit as y goes to 0 of 12 sine squared 2y times the cosine of 3y divided by the sine of 3y. We are now going to isolate our sine functions. We have a sine squared of 2y. It's in the numerator. Let's isolate it. It's being squared, so we're going to be squaring the quantity. We have a sine 3 theta. It's in the denominator, so we'll put it in a denominator. And then we have left over a 12 cosine of 3y. We'll put that in its own fraction. Now, the sine of 2y to phase match, we have sine of phase 2y in the numerator. We need a 2y in the denominator, and we're going to compensate this by multiplying the last fraction by 2y, but notice it's being squared, so we have to put in a 2y squared. So now it's phase matched. Now we need to phase match the sine of 3y. The sine with a phase of 3y in the denominator needs a 3y in the numerator. So we'll put that there, and then we'll compensate by putting a 3y in the denominator in the other fraction. And now that one's been phase matched as well. Our next step is to simplify the other fraction. So we'll leave these sine fractions the way they are. They are perfectly phase matched, and we'll be able to make use of the identity. But then we also have this last fraction, and it's 2y quantity squared, which is 4y squared times a 12, which will be a 48y squared cosine of 3y, and then divided by 3 and a y. Now one of the y's can cancel, since they're all multiplying each other in the numerator and denominator with other things. So we'll cancel those out. And then the 48 and the 3 can cancel to a 1 here and a 16 here. Let's make sure we remember that y that's right there as we rewrite this. So we'll have limit as y goes to 0 of cosine of 2y over 2y quantity squared times 3y over the sine of 3y. And we're left with a 16y cosine of 3y, and it's all over a 1, which we therefore do not need to write. And now we can make use of the identities. Each of these phase-matched signs are going to have a limit equal to a 1, so that'll be here and here both. And that means we have 1 squared times a 1, and we no longer have the 0 over 0 indeterminate form. We can plug a 0 in for the remaining y's, which will be a 16 times a 0, and then a cosine of a 3 times a 0. Now 1 squared times 1 is 1. 16 times 0 is a 0. And then cosine of 3 times 0 is a 0. 1 times 0 is 0, and then cosine of 0 is a 1. 0 times 1 comes out to 0.